We navigate our lives every single day using maps on our phones, right? We just trust them completely to get us exactly where we need to go. But what happens when the very shape of the world that those maps are based on is called into question? Welcome to This Explainer. Today, we're going to dive into a deeply human, honestly really practical mystery right at the center of the modern flat Earth debate. We're looking at our fundamental need to accurately map our shared reality. So after nearly 20 years of the modern flat Earth movement gaining, immense traction online, there's a glaring question that just cuts right through all the noise. And it's this: why hasn't a working map been produced? And I don't mean just an artistic sketch. We're talking about an actual, functional, mathematical map. It's a beautifully simple question, but it literally tests the limits of reality itself. Because think about it, a map is way more than just a pretty drawing with some coastlines and a compass tucked in the corner. It's actually a strict mathematical promise. Every single point on it has to represent a known, measurable location. Reality has already decided the exact physical distance between, say, London and Paris. You don't really get to have an opinion on that distance. A true map simply reflects that undeniable math, regardless of what anyone believes.
Now, there is a crucial difference here that often trips people up. Yes, traditional globe maps, like the famous Mercator projection everybody knows, they do contain known distortions. Cartographers have known for centuries that flattening a 3D sphere onto a 2D surface requires stretching something. But if the Earth is already a flat plane, you shouldn't need a mathematical projection at all. You would literally just draw exactly what physically exists.
Section 1. The Gleason Map. The best guess. So when examining the most frequently cited model in the movement, the go-to answer is almost always the Gleason Map from the late 1800s. It centers right on the North Pole, and it turns Antarctica into this massive ice ring around the outer edges. But here is the ultimate irony. Alexander Gleason didn't create this by proving the Earth was flat. It's actually just a standard mathematical projection of a globe onto a flat piece of paper, originally created by globe cartographers. It literally starts by assuming the Earth is a sphere.
Okay, but does it actually work in reality? Well, the first massive discrepancy is Antarctica. By stretching the continent into a giant ring around the entire edge of the world, this map demands a coastline that is vastly longer. We're talking thousands and thousands of kilometers longer than reality. And we know this for sure because actual human beings, sailors braving freezing waters and explorers charting courses, have physically sailed and measured a dramatically shorter coastline. The math here simply betrays the human experience.
Section 2. The Southern Hemisphere Problem.
This is where the map truly breaks down, when we look at how actual people travel. If you look at the Northern Hemisphere, say a flight from London to New York, the distances seem perfectly fine on the Gleason map. But look south. Because all those southern continents are stretched so far outward toward the edge of the disk, the distances between them become wildly distorted. This makes real-world shipping lanes and commercial flight routes mathematically impossible.
Let's put a concrete number on that just to see how distorted it gets. On a globe, the flight that thousands of regular passengers take every single year from Sydney to Santiago is roughly 11,000 kilometers. It's a long journey, absolutely, but it's perfectly achievable. But on the Gleason map, because those two cities are pulled so incredibly far apart towards the outer edge, that distance explodes by thousands of extra kilometers. The map fundamentally disagrees with the physical travel time of regular people.
Now you might be wondering, why not just tweak the map? Move Australia a little bit at just South America? Well, people have been trying to do exactly that for decades. The issue is that fixing one part inevitably breaks another part. It is basically an endless game of geographical whack-a-mole. If you fix the distance between Sydney and Santiago, suddenly the shape of Africa is completely ruined. The problems don't actually disappear, they just shift to somewhere else on the paper.
Section 3. The 4 Rules of Reality.
To cut through all the complex arguments about space or satellites, we can rely on a remarkably simple challenge. A functional map must simultaneously satisfy 4 basic conditions. It needs correct continent shapes, correct continent sizes, correct distances between places, and correct directions. Trying to meet all 4 of these at the exact same time on a flat model is basically like trying to draw a square circle. The moment one becomes correct, another instantly breaks.
Now, people often argue that globe maps are distorted too, and yes, they absolutely are. But science is entirely transparent about this. Cartographers know a map might heavily distort the size of Greenland, but they use it strictly because it's brilliant for ship navigation. The vital difference is that all those slightly distorted scientific maps are simply different tools relying on one single underlying globe model. Flat Earth models, on the other hand, aren't just choosing a projection. They're attempting to describe the actual physical shape of the Earth itself, but they completely lack that single unified baseline that always works.
Section 4. The true test of science.
So what actually makes a scientific model useful for humanity? Well, models aren't judged by how passionately they're defended. They aren't judged by how many millions of internet views they get or how strongly someone believes in them. They are judged on one thing and one thing alone: do they successfully predict what we observe in reality? Billions of people rely on globe-based maps every single day without even thinking about it, simply because they work.
And this perfectly illustrates how human knowledge actually progresses. We don't just throw out older models in a fit of rebellion, we refine them. We still use Newton's laws to build bridges and calculate concrete today, even though Einstein refined those models over a century ago. Why? Because for everyday human tasks, Newton's model works brilliantly. Science recognizes where a model stops being accurate and improves it. It doesn't just pretend older functional models were totally useless.
This really reframes the entire debate. If a brand new, fully worked out flat Earth map actually existed tomorrow, one that flawlessly met all 4 of those mapping conditions, scientists wouldn't hide it. They wouldn't ignore it. They would celebrate it as one of the most monumental discoveries in human history. Universities would test it. Mathematicians would eagerly pull it apart to see how it worked, because science always, ultimately, champions the model that best explains our shared physical reality.
So before getting tangled in heated debates about gravity, NASA, or ice walls, ground the conversation in something incredibly tangible. Leave the complex physics aside for just a moment and ask this one undeniable question: can I see your map? Because if a model cannot provide a map to accurately guide us through our own backyard, how can we trust it to explain the universe? Thanks for joining this explainer. Keep questioning, keep learning, and I'll catch you on the next one.